Chapter 22, Easy Buffer, Finding the pH of a Buffer. What is the pH of a buffer that is 50 milliliters of 0.5 molarity ammonia mixed with 50 milliliters of 0.2 molarity ammonium chloride? So here we have a weak base and what should be its salt. And this problem in your notebooks, it does not have the Kb, however I'm providing it for you. Here it is. The Kb of NH3 is 1.75 times 10 to the negative 5. Alright, so first let's do what we always do. Identify, oops, that should be a Y, major species. Alright, so we are working with ammonia, which we know is a weak base, and ammonium chloride, which we know is a salt, and we know that because we have a cation with an anion. Step 2, write out the reaction. So we're going to show ammonia, and by now you might be able to predict that we need to add water to it in order to show where this hydrogen comes from, and that leaves us with a hydroxide. Then we will take our salt, and since salts dissociate in water if they are soluble, which this one is, NH4 plus Cl minus. Alright, step 3. Since we have a reversible reaction up here, we're going to write out our equilibrium expression. So I know that ammonia is a base, so I'll have a Kb, and I'll have NH4 plus. Now remember, this is a buffer, OH minus, so some of those ammonium ions are going to be supplied by that salt, which is going to cause it to not use up as much of the ammonia in the reaction. Alright, so let's see, what's our Kb? It's given 1.75 times 10 to the negative 5. Alright, step 4. What we need to check now is, has it been diluted? Because if so, we need to do a dilution. We are mixing 50 milliliters of one thing with 50 milliliters of another. So, yep, we need to do a dilution. So we'll have one for each substance. So here's our ammonia. It'll be 0.5 molarity times its initial concentration of 50 milliliters is equal to M2 times its new concentration. It got added together. So our ammonia is 0.25 molarity in this buffer initially. At equilibrium, it might be different. So our ammonium chloride, that one started out at 0.20 molarity and 50 milliliters. Oops, I don't know why sometimes I write milliliters and sometimes I don't. I'll try to be more consistent. Okay, so M2 is equal to 0.10 molarity. And this is our ammonium chloride, which we know dissociates completely in water, so I can split this up into its pieces and say, oh, I've got that concentration of ammonium, which is really what we're interested in, because it affects our equilibrium up above. Alright, so now we are going to use this information to set up our ice chart. So ICE, and I'll just write it for my base. And remember, we have a common ion here between the ammoniums. So that affects our ice chart. So I know my initial concentration of ammonia is 0.25, and I know my salt has provided 0.10, and I don't have any hydroxide at the start. My water is left out. Oops, I didn't put it on here, and I usually do. I'm sorry, water, I forgot you. Okay, water gets left out. All right, so for our change, so this is a weak substance that bounces back and forth. We don't know any equilibrium numbers, so we'll have to use our x's. So 0.25 minus x, x, x. All right, now that we've got our x's figured out, let's plug into our equilibrium expression. So 1.75 times 10 to the negative 5 is equal to x. Oh, I forgot something up here. Let's see. This should be 0.10 plus x for the ammonium. So we'll have x from the hydroxide times 0.10 plus x from the ammonium all over 0.25 minus x. Let's go ahead and use that small x assumption. So assume x is small, which allows me to cross off any x that is being compared to something via addition or subtraction. So that one's gone, and that one's gone. So this allows me to find that x is equal to 4.38 times 10 to the negative 5. And let's go ahead and say, all right, that is also equal to the molarity of our hydroxide. We could use it to figure out the other concentrations too, which we will soon. But first, let's just check that our assumption is valid. So 4.38 times 10 to the negative 5 over what it's being compared to. I'm going to pick the smaller of the two because that's the harder test to pass. And if you ever forget that, just test both of them. All right, let's plug that in. Times 10 to the negative 5 divided by 0.1 times 100. It's still a very small number, so we will be good. This is equal to 0.0438%, which is less than 5%. So that's good. Excellent. All right, so now we know this is a buffer, which means that we need to use if we're going to solve for pH, we need to use the Henderson-Hasselbalch equation, which means we need more concentrations. So I know the concentration of my hydroxides. I could also find the concentration of my ammonium, which would be 0.1, here I'll say that here, NH4 plus 0.10 plus X. And the concentration of my ammonia is going to be 0.25 minus X. I'm going to just leave them like that for now so that the rounding is better later. But if you went ahead and solved for those concentrations now, that would not be a problem. Okay, so solve for pH. Remember, it's a buffer, so if you want to solve for pH, you need to use the Henderson, Hasselbalch. So I know in this equation that if I am working with a base, I want to say POH is equal to the negative log of the Kb plus the log of the base. Actually, I think it'd be the other way around. Hb minus of the ion over the the original base. Okay, so POH is equal to negative log, we know our KB, it was given, 1.75 times 10 to the negative 5 plus the log of our ion, so that's ammonium, so 0.10 plus 4.38 times 10 to the negative 5 over our original 0.25 minus 4.38 times 10 to the negative 5. And I'm realizing when I say the original that might confuse people. I'm not talking about the original concentration of ammonia. These are both supposed to be equilibrium concentrations. Both of these are equilibrium concentrations. All right, so I'm going to go ahead and plug this in my calculator, and you can do this along with me so you're not bored. Negative log 1.75 times 10 to the negative 5 plus the log of 0.1, whoops, oh no, plus the log of, I'd really like to have one of those fancy pants graphing calculator apps on my computer so you could watch me plug these in. That would be nice. I don't have that though, so oh well. Divided by 0.25 minus 4.38. Okay. There it is. All right, so I got a POH of 4, and let's see, how many sig figs should we have here? Looks like probably want 2, based off of that 0.10 and 0.25. So 4.36. However, this problem is asking us to solve for the pH, but that's not a problem. We can do that. pH, assuming this is at 25 degrees Celsius, you should end up with 9.64 is your pH. So that's how you'd solve a buffer problem. You would write out an equilibrium expression, do the dilution, use the ice chart to figure out the concentrations that you can then use to solve for X using the equilibrium expression, which you can then use to solve for concentrations, which you can then use in the Henderson-Hasselbalch equation to solve for pOH or pH.